Hello students. So last class we did how to convert a binary number into an octal number. We learned this by doing 3-bit synchronization. If you had a binary number, we had to group them into threes starting from the rightmost side. The rightmost side is supposed to be the least significant bit, LSB. And the leftmost side is supposed to be the most significant bit, MSB. So today we will learn the conversion from binary to hexadecimal. I had given you all a hint last class that it is the same technique of binary to octal. We'll use the same technique, but we will be doing 4-bit synchronization. The reason is very simple. Hexadecimal is a 16-base number system. And so, if you want to convert a binary number into a hexadecimal number, 4 bits, that is 2 raised to 4, is more than enough, is sufficient to represent one hexadecimal number. So we will be doing the same method, but with 4 bits instead of 3 bits. Let's begin. So let's say I do have a number 1, 1, 0, 0, 1, 0, 1. I have to convert this into a hexadecimal value. So first we are going to group them into 4s. So my one group is here. Second group will be this, and I'm going to add a 0 over here. Now I have to convert this to its binary equivalent. So I will write 1, 2, 4, and 8. Okay. Here also 1, 2, 4, and 8. Now what we need to do? We are going to find the number. So this is 5. This is 6. So this is 65 in the number system hexadecimal base 16. Yes? Have you understood this? We'll do one more just so that you understand this better. Let's take another number. That's a pretty large number. So let's give it a try. Okay, so I'm going to trying to change the color. Okay, fine. So we're going to group them into 4s. So 1, 2, 3. And for the 4th one, I'm going to add 3 zeros. All right. Now, if you look at this one, 1, 2, 4, and 8. So this will give me the number 2. Again, 1, 2, 4, and 8. This will give me the number 1 plus 4, 5. Again, 1, 2, 4, and 8. This will give me 8 plus 4, 12, 13, 14. Now, when I write 14 here, remember, this is hexadecimal. So 14 is represented by the alphabet E. And this will be 1. So the answer will be 1, E, 5, 2 to the base 16. Yes? Okay. So can we practice this today? Can I give you all some numbers and will you all convert it? All right, let's give that a try. Let me write down some numbers here. Okay, that's the first number. Convert it into a hexadecimal number and let me know the answer. You all have exactly 1 minute to solve this. Have you all been able to do it? I'll tell you all the answer very soon. This is the second number. You all should start trying. The first answer is 7249. Of course, with the brackets, base, with the brackets, base 16. The second answer, I'm going to write the answer very soon. So please do your conversions and keep. You all know if you think it's going too fast, you all can always pause, solve, and then check. Okay, the answer is this was the question, and the answer is this 1AF67. When the number remainder is, when you get the decimal equivalent 10, you should convert it to A. When you get decimal equivalent 15, you must convert it to F. Shall I give you one more? Okay, let's take one more then. Okay, let's convert this one. The last one for today. Come on. Sometime more. All right. I'm putting the answer up. So if you want, you can pause if you're still solving it. The answer is this: B, C, A, F. Don't forget to put the brackets and write the number 16 at the bottom to indicate base 16. Okay. So now, y'all should also learn how to convert a hexadecimal number into binary or an octal number to binary. Can you think how you would do that? Yes, you just have to reverse it. Yes. So if let's clear all the truth. Let's say I have an octal number. Just give me a minute. Or let's take another hexadecimal number only. Let's enter the hexadecimal number. So let's take, I have an hexadecimal number 45F5. I want to convert this to binary. So how will I do it? It's very, very simple. I'm just going to write the binary equivalent for each of these numbers. Okay, so we will start with, let's say, the number 5. So how will I write 5 in a 4-bit? That means in 4 characters, in 4 numbers in the binary form. To write 5, I will have to put, I'll have to do 0, 1, 0, 1. I'll tell you all how I got this. If you are confused in this, I will just show it to you. I'll give me a minute. So you remember the binary 1, 2, 4, 8. Yes. So 4 and 1. So I'm going to write 1 here. I'll write 1 here. And the other places will go as 0. And this will become my 4 bits that represent 5. Okay. Now comes F. How will I represent F? F is nothing but 15. Correct? So 8 plus 4, 12, 13, 14, 15. So it will be 4 times 1. Correct? Again 5 will again be 1, 0, 1, 0. If you look reverse. And finally, I have to write 4. How will I write 4? 0, 1, 0, 0. So this entire thing together is my hexadecimal number. If I have to write it, I will write 0, 1, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, 0, 1, 0, 1. And if I will sit and convert this back to my hexadecimal, I will get 4, 5, F, 5. Yes? So, just give me a second. Yes, so we had stopped here where we did a conversion from hexadecimal to binary. Now we will continue further, and I want to do a quick recap on the chapter. And after that, we will end today's class.
Number system and introduction. Why learn the number systems? We humans speak in a particular language. This language is made of words and letters. Although we type words and letters in the computer does not understand the words and letters. Rather, those words and letters are translated into numbers. A computer can talk and understand in numbers. That too in only two numbers, called binary numbers. Why computers use binary number system? A computer needs to convert the instructions giving languages to binary number system. Binary number system is used by computers because a computer can understand only two states, that is, presence and absence of the electrical pulse. A binary digit is called a bit. There are two possible states in a bit, expressed as 0 and 1. And these are the two numbers used in the binary number system. A bit could represent on, off of an electrical circuit. Yes, no, true, false, 0, non-zero, or similar two states or binary wording. Since computers work on electricity, we can use these two states only to represent each number or character. A series of 8 bits makes a byte. This is an ordered sequence of 8 bits that can represent one of 256 or 2 to the power of 8 possible values. So, a byte of memory can store a decimal number in the range 0 to 255. These are good enough to represent all the printable and non-printable characters. The ASCII code is developed to represent all characters, including capital and small alphabets, numbers 0 to 9, punctuation marks, and any other special characters. Why octal and hexadecimal number systems? Octal and hexadecimal numbers are a convenient way to represent binary numbers used by computers. Computer mechanics often need to write out binary quantities. But in practice, writing out a binary number such as 100, 100, 110, 101, 0001 is tedious and prone to errors. Therefore, binary quantities are written in a base 8 octal or much more commonly a base 16 hexadecimal or hex number format. This is why you need to understand the 4 most common number systems that are frequently used in computers. These number systems are binary, octal, decimal, hexadecimal. If you have an understanding of the number systems, you will understand how the computer converts each number or character into binary and performs the required operations. Understanding number systems. A number can be represented with different base values. The base of any number system is determined by the number of digits in the system. You are familiar with the decimal numbers. In the decimal number system, there are 10 different numbers: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Hence, the base is 10. A computer uses a binary number system, which can have only two values, 0 and 1. Hence, the base is 2. A decimal number with a few digits can be expressed in binary form using a large number of digits. Thus, the number 65 can be expressed in binary form as 1000001. An octal number with base 8 makes use of the 8 digits 0, 1, 2, 3, 4, 5, 6 and 7. The binary form can be expressed more compactly by grouping 3 binary digits together to form an octal number. A more compact representation is used by hexadecimal representation, which groups 4 binary digits together. It can make use of 16 digits, but since we have only 10 digits, the remaining 6 digits are made up of first 6 letters of the alphabet. Thus, the hexadecimal base uses 0, 1, 2 up to 8, 9, A, B, C, D, E, F as digits. The table below shows a comparison of the first 16 numbers in the binary, octal, decimal, and hexadecimal number system. Analyze these numbers using the relationship between digit, base, and position. Notice that a binary 10 is the same as a decimal 2, that an octal 10 is the same as a decimal 8, that a hexadecimal 10 is the same as a decimal 16, that each hexadecimal digit has corresponding 4 bits in binary system. Each octal digit has corresponding 3 bits in binary system. You can represent the binary notation from the hexadecimal number by grouping 4 binary digits per hexadecimal digit, or from the octal number by grouping 3 binary digits per octal digit, and vice versa. Each group can be converted to a single number by giving the powers of 2. Convert from any base to decimal. In the decimal, binary, octal, and hexadecimal systems, the value of any digit in a number depends on its position within that number, that is, the place value of the digit. The significance of place value. The order of the digits is significant, according to which it carries the weight. The positional value is based on the powers of the number system's base value. The formula to convert from any base to decimal is digit into base, position, number. Let us analyze the decimal number 345 to understand that how a number system works on positional values. Observe that 3 is the most significant digit. It carries the most weight, and 5 is the least significant digit. It carries the least weight. The first digit of this number is 3, but because this digit is located in the hundreds column, you know it really represents the value 3 into 10 to the power of 2, or 300. It is the most significant digit as it carries the most weight. Similarly, the 4 in the tens column represents the value 4 into 10 to the power 1, or 40, and 5 is the least significant digit and carries the weight of 10 to the power of 0, which is 1. So, it has the value of 5 into 10 to the power of 0 equal to 5. Remember that any base to the power of 0 is equal to 1. This is the same for each number system. The least significant digit has a value of base to the power 0 equal to 1, increasing to base to the power of 1 for the next digit, base to the power of 2 for the next, and so on. We distinguish between various number systems by putting a small subscript after the number to indicate the base. For example, a typical decimal number would be written like 465 base 10, and a typical binary number would be written like 11011 base 2. This works well with binary and octal systems, and you have practiced in previous class. What about the decimal equivalent of the hexadecimal number 33b base 16? convert the hexadecimal number to decimal. Let us convert the hexadecimal number 33b base 16 to decimal notation. Since you are using a base 16 number system, the columns of your table are now powers of 16.
So we were converting 33b from hexadecimal to decimal, and we know this is going to be raised to the power of 3. So we will have, you will have 1, then you will have 16, and then you will have 256. Yes, 16 raised to 2. Yes, to be 2, 256. Yes, okay. So what is it going to be? B is number 11, correct? So this will be 11. Sorry. This will be the number 11 plus 3 into 16. So this we will add 48. Yes. And then 3 into 2, 56. So what will we add over here? 768. Take the number, add it. 827. The answer is 827 in the base of 10. Okay. This is how you convert a hexadecimal number into decimal equivalent. Okay. With this, we end today's class. I will be leaving some worksheets in the description box. Please solve those. See you all tomorrow. Take care. Stay home, stay safe, and keep learning.